Hi Year 12, this is our fourth lesson for the topic of proof for Extension 2 Mathematics. In this lesson we're going to look at inequality proofs. So far we've learnt about the language and notation with logic, direct proof, and then last lesson we covered indirect proof, including proof by contradiction and proof by contraposition. So let's have a look at some properties of inequalities that could be useful in our proofs. So the first one, and these are all fairly obvious. We can add and subtract the same number from both sides of an inequality. So suppose we have got A is greater than B, then it follows that A plus K must be greater than B plus K. We can multiply both sides of an inequality by a positive number and nothing changes. If we multiply both sides of an inequality by a negative number, then the inequality sign will be reversed. If we take the reciprocal of both sides, and if both sides are positive, then the inequality sign will be reversed. And finally, if both sides of an inequality are positive, then we can square both sides. Now I would suggest that you try a numerical example with each of those and make sure that they all make sense to you. Now inequalities of the same type can be linked together. For example, if A is greater than B and B is greater than C, then A is greater than C. They can be multiplied together. Example, if A is greater than B and they're both positive, and C is greater than D and they're both positive, then AC is greater than BD. And they can be added together. If A is greater than B and C is greater than D, then A plus C is greater than B plus D. However, there is no general rule where inequalities can be subtracted from one another or divided into one another. So here's our first question. Prove A over B plus B over A is greater than or equal to 2 for all real numbers A and B that are greater than 0. So A and B are both positive. I'm going to show you two methods to do this, and you should be familiar with both of these methods. The first one, we want to take everything over to the left-hand side and prove that the statement is greater than or equal to 0. So I'm going to start with a required to prove statement. I want to prove that A over B plus B over A minus 2 is greater than or equal to 0. Now, this is much easier to prove something's greater than or equal to 0 than greater than or equal to 2. So that's why we do it. Now I'm going to start with the left-hand side. We don't put this inequality in yet because we don't know that this is true. We're trying to prove that that's true. So we start from the left-hand side and work towards the right-hand side. Okay, what can we do? Let's make a common denominator of AB. Now, do you recognize this numerator? That's a perfect square, isn't it? It's A minus B all squared. We've actually finished. This here is positive because it's a perfect square and A and B are both real, and A and B are both positive. So now we put in the right-hand side. It's greater than or equal to 0 since A and B are both positive. Now our second way of doing this is to start from the identity A minus B all squared is greater than or equal to 0. And I've written there that it's a very useful identity. It's only ever the negative. A plus B all squared being greater than or equal to 0 doesn't give us much at all. So it's always A minus B all squared is greater than or equal to 0. And in this case, I'm going to start with that both sides because that's a true statement. I'm not working from the left-hand side to the right-hand side. I'm stating this as a fact. A minus B all squared is greater than or equal to 0 because A and B are real. Now let's expand that out. Having a look at what we want, can you see we want the 2 over the other side? So I'm going to take this over here. A squared plus B squared is greater than or equal to 2AB. Now let's divide through by AB and we actually get the identity that we want. So A over B plus B over A is greater than or equal to 2. Now if we've done anything here that we should explain, when would this not work, what I just did? If A or B were negative, I would flip the sign. So we should say this is true since A and B are positive. Let's have a look at a past HSC exam question. By considering the right-angled triangle below or otherwise, prove that A plus B all over 2 is greater than or equal to the square root of AB, where A is greater than B and they're both greater than or equal to 0. So we can do this two ways. We can use the right angle triangle, or we can do it another way. So I'm going to show you both methods. We're going to use a method similar to what I just did first, and then we'll do it using the right angled triangle. Okay, so I'm going to start by taking the square root of AB over to the left-hand side and writing a required to prove statement. I want to prove that A plus B all over 2 minus the square root of AB is greater than or equal to 0. Okay, let's start with the left-hand side. A plus B all over 2 minus the square root of AB. Making a common denominator of 2, I end up with this. Now this is actually the square root of A minus the square root of B all squared. Now have a look at that for a second. And this brings us to a really important point. I said before that A minus B all squared being greater than or equal to 0 is a really important identity. It is, but there are other versions of it. We can make any substitutions here that we like. You can just see one there that I've done. But we could also do A squared minus B squared all squared is greater than or equal to 0. Or we could do xy minus yz all squared. That would also be greater than or equal to 0. So don't limit yourself just to this. You can make any substitution for A and B that you like. But of course now we are finished, aren't we? Because square root of A minus the square root of B all squared, that is greater than or equal to 0 because A and B are both real. Now let's do this question using the right angle triangle. What springs to mind when you see that triangle? Hopefully you're saying Pythagoras' theorem. Using Pythagoras' theorem we get x squared is equal to A plus B all squared minus A minus B all squared. Expanding it out and simplifying, x is equal to 2 root AB. Now from the properties of a triangle, a right angled triangle, the hypotenuse can never be less than another side. So A plus B must be greater than or equal to 2 root AB. And we're nearly there, aren't we? Divide both sides by 2 and we're done. Here's part 2. Prove that p squared plus 4q squared is greater than or equal to 4pq. With these sorts of questions, we should always be using whatever they've given us in part 1. So this is the clue. But how do we get from here to here? We're going to use another really well-known technique, which is substitution. See this plus here, p squared plus 4q squared? It's kind of like the a plus b. So I'm going to substitute p squared for a and 4q squared for b, like this. You can see this time I've actually written the inequality. Because we're coming from something that is true, we can write the whole thing down and just try and turn it around until we get this. Hope that makes sense to you. All right, what do we need to do? Let's take the 2 over the other side and we can tidy up under this square root. And this is actually equal to 2pq, isn't it? So there's the answer. Okay, moving on. Recall that the arithmetic mean of two numbers a and b is given by a plus b all over 2. And the numbers a plus b all over 2, and b form an arithmetic sequence. But there's another type of mean, it's called the geometric mean. The geometric mean of two numbers a and b is the square root of ab. So we multiply them together and then take the square root. And not surprisingly, the numbers a, square root of ab, and b will form a geometric sequence. Now the arithmetic mean of two positive real numbers is greater than or equal to the geometric mean, and this is called the AM-GM inequality. In other words, for a and b, where a and b are positive real numbers, a plus b all over 2 is greater than or equal to the square root of ab. So let's look at a past exam question. For all non-negative real numbers x and y, the square root of xy is less than or equal to x plus y all over 2. And that, of course, is our AM-GM inequality. And it says do not prove this. But using this fact, show that for all non-negative real numbers a, b, and c, the square root of abc is less than or equal to a squared plus b squared plus 2c all over 4. Okay, let's compare. How are we going to get from here to here? Looks like we need to do some sort of substitution. So let's let x equal AB and y equals c. And that gives us the square root of ABC on the left-hand side, which is what we want, is less than or equal to AB plus c all over 2. We're not quite there, are we? All right, I can see I want a denominator of 4, so let's make that happen. That's equal to 2AB plus 2c all over 4. So now I've got the 2c that I want. But how do I turn 2AB into this? Is it ringing any bells for you? A squared plus b squared and 2ab. It should be, because we know that a minus b all squared is greater than or equal to 0. Expanding that out, we get a squared plus b squared is greater than or equal to 2ab, or more importantly, 2ab is less than or equal to a squared plus b squared. But how do we get from here to here? We know that 2ab is less than or equal to a squared plus b squared, so it follows that 2ab plus 2c all over 4 is less than or equal to a squared plus b squared plus 2c over 4. Now have a look at the notation here. I started with this, and then I said, well, this is equal to this. I've just changed it around, so I used an equal sign. But then this is less than or equal to this, and that's why I've used this sign here. So I've proven it. Square root of ABC is less than or equal to a squared plus b squared plus 2c all over 4. Part 2. Using part 1 or otherwise, show that for all non-negative real numbers a, b and c, the square root of abc is less than or equal to a squared plus b squared plus c squared plus a plus b plus c all over 6. Okay, so using this part here. Now we want to introduce a c squared. So I'm going to do 3 versions of this. The one where it's a, b and c, and then the one where it's b, c and a, and the one where it's A, C, and then B. Okay, so I've just done different substitutions there. Now I'm going to add all of those together. That's going to give me 3 lots of the square root of ABC is less than or equal to a squared plus b squared plus 2c plus b squared plus c squared plus 2a plus a squared plus c squared plus 2b all over 4. Okay, let's tidy that up. We have 2a squared plus 2b squared plus 2c squared plus 2a plus 2b plus 2c. And if we bring this 3 over and cancel the 2 into the 4, we end up with the inequality that we want. Now we can actually generalize that AM-GM inequality to apply it to n numbers. So that means that the arithmetic mean of n numbers will always be greater than or equal to the geometric mean for n numbers. Let's finish off this section with a past exam question. It is given that for positive numbers x1, x2, x3, xn with arithmetic mean a, x1 times x2 times x3 times times xn all over a to the power of n is less than or equal to 1. Do not prove this. Now this of course is our extended AM-GM inequality, but it's written in a really weird way. Suppose a rectangular prism has dimensions ABC and surface area S. Show that ABC is less than or equal to S over 6, all to the power of 3 halves. Now it's pretty hard to see how this is going to come from this. But we do know a formula for the surface area of a rectangular prism. So let's start there. S is equal to 2 lots of AB plus AC plus BC. Or S over 2 is equal to AB plus AC plus BC. Now, instead of using this version of the AM-GM inequality, I'm going to use my normal version. In other words, that the arithmetic mean is always greater than or equal to the geometric mean. And I can kind of see this is a little bit like this numerator here. So we've got 3 terms, n is going to be 3, and I'm going to let x1 equal AB, x2 equal AC, and x3 equal BC. So substituting in, we get this. AB plus AC plus BC all over 3 is greater than or equal to the cube root of A squared, B squared, C squared. And tidying this up, that is equal to ABC all to the power of 2/3. Now we're close, aren't we? Because AB plus AC plus BC is equal to S on 2. And so S on 6 is greater than or equal to ABC all to the power of 2/3. And now to get to here, all we need to do is raise both sides to the power of 3/2. And that will give us the answer. This and like this, because that is equal to 1. I'm going to flip it around as well. Therefore, ABC is less than or equal to S over 6 all to the power of 3/2. Okay, my top tips. Move everything to the left-hand side and prove that the expression is greater than or equal to 0. Or start with A minus B all squared is greater than or equal to 0, or some version of that. Substitute into a known identity, and this includes multiple variable substitution. So where you substitute A and B, and then B and C, and then A and C, and you add them all together. Okay, let's finish off with the triangle inequalities. There are 2 triangle inequalities, and they are very useful. The first one says that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. And the second one says that the absolute value of x minus y is greater than or equal to the absolute value of x, take away the absolute value of y. Okay, so let's look at the geometric proof of that first triangle inequality, and then we'll have a look at the algebraic proof of the same inequality. Consider triangle OAC, which is here. We know that the length of OC must be less than or equal to the length of OA plus the length of AC, and that's just the properties of a triangle. But we also know that vector AC is the same as vector OB, and they have the same length. We also know that vector OC is the vector addition of OA and OB. So let's substitute both of those facts into here. So instead of vector OC, we have vector OA plus vector OB. And instead of the length of vector AC, we have the length of vector OB. And this is actually the same as this. Can you see? Instead of vector OA, I'm just going to write X. Instead of vector OB, I'm going to write Y. And there's our proof. Now let's look at the algebraic proof. I'm going to start with this rather strange statement. It says that X lies between the negative absolute value of X and positive absolute value of X. That's true, isn't it? Similarly, Y lies between negative absolute value of Y and positive absolute value of Y. Okay, let's add those two together. We end up with negative absolute value of X plus negative absolute value of Y is less than or equal to X plus Y is less than or equal to absolute value of X plus absolute value of Y. Factorizing here, we have negative and then brackets absolute value of X plus absolute value of Y. Everything else is the same. Now I'm going to use this. Do you recall that if we write absolute value of X is less than or equal to K, this really means X lies between negative K and positive K? That's what we have here. Do you see? So we can rewrite this as absolute value of X plus Y is less than or equal to absolute value of X plus absolute value of Y. Okay, so your turn. Have a go at proving the absolute value of X minus Y is greater than or equal to absolute value of X, take away the absolute value of Y. You can choose to do it geometrically or algebraically. All right, that's it for this lesson. Next lesson is on further mathematical induction.